Today, we're going to talk about entropy. First of all, what is entropy? Entropy is often defined as a measure of disorder of a system. For example, imagine a glass of liquid water and a solid ice cube. Liquid water has a higher entropy than ice. If we zoom in on the molecules, this becomes more clear. The molecules of water are fluid and more spread out, while the molecules in ice are structured, rigid, and do not have the opportunity to become more disordered. A gas would have even higher entropy than both of these systems.
Although commonly known as a measure of disorder, this is not exactly what entropy is. Entropy is actually a measurement of probability. More specifically, it is the probability of energy spreading out. A system having a low entropy contains energy that is highly concentrated in one area. It is extremely unlikely that the energy of a system will become more concentrated spontaneously. By spontaneous, we mean a reaction is thermodynamically capable of happening without outside energy to move it along. Higher entropy means the energy is distributed over a wider area and has the ability to spread out freely. For example, imagine a flame on a candle. The flame does not spontaneously get hotter and hotter. Rather, the energy spreads out and the flame fades.
The formula for the statistical definition of entropy is S is equal to K times the natural log of W. This is known as the Boltzmann formula. S is entropy, K is a constant, and W is the number of microstates. This is the number of configurations or ways you could arrange the energy of a system. When the number of microstates is 1, entropy is equal to 0. This is because there is only one way the energy can be arranged in that system. There is no probability of the energy spreading out. As the number of microstates increases, the entropy increases as well.
Now to talk about some thermodynamics. We will now be talking about the change in entropy. The equation for the change in entropy is ds is equal to dq, where q is the heat absorbed over T, the change in temperature. This would be for a non-constant temperature and a reversible process. Delta S is equal to Q divided by T when the temperature is constant. If we wanted to calculate the change in entropy from state A to state B, we could do this integral. We replace ds with dq over T and find the entropy of the reversible process from A to B. Another fun fact about entropy is that it is a state function. If we take a look at this mountain, there are many ways you could climb it to reach this flag. You could climb up the mountain in a straight line, or take the windy path up. Either way, for a state function, it does not matter how you arrived at the endpoint.
Entropy is also related to free energy. We can see how much work is performed by a thermodynamic system using Gibbs free energy equation. A highly positive change in entropy will result in a very negative change in the free energy, or delta G. A negative delta G means that work is being done on the system and is therefore energetically favorable. A negative change in entropy will result in a positive delta G, which is energetically unfavorable. Now let's talk about the second law of thermodynamics, which states that the entropy of the universe is always increasing. For example, think of a cup of coffee with milk. Over time, the hot coffee and cold milk mix together to become one uniform mixture. Now, why does the universe favor entropy? There's a set amount of energy in the universe which started out concentrated all in one small space. This was the Big Bang. Since then, the universe has continued to expand, constantly spreading out what energy exists. And as we said earlier, entropy increases when energy spreads out. So because the universe is constantly expanding, the total entropy of the universe is always increasing.